Today I'm going to talk about self-shrinkers for mean curvature flow, their entropy and index, and how we can compute these quantities and use the results of these computations to help us prove things. So this talk is going to be split in 4 videos. You're watching the first one, in which I will give a brief introduction of mean curvature flow self-shrinkers. In the second video, I'll give a brief introduction to the entropy of self-shrinkers and discuss some results. In the third video, I will give a brief introduction to on stability and index of self-shrinkers and discuss some more results. And finally, in the last section, I'm going to present some references and discuss several future directions for this work. So let's begin. To introduce mean curvature flow, it's often easiest to start with the one-dimensional setting, which is curve shortening flow. So I've borrowed a picture here on the left that illustrates how curve shortening flow works. So you have this curve. You can imagine it's a rubber band that's trying to become shorter. And the way it moves is the more curvature there is, the faster it will move. So you can see this point has a lot of curvature, and so it will move very fast under curve shortening flow. Likewise, this point is also very curved, and the curve will move very fast under curve shortening flow. And this point here, there's not much curvature, and so this point will not move much or at all under curve shortening flow. Overall, the length of the curve will decrease as we move along the flow. To the right, I'm going to present a video from Angenent. And this illustrates a very stark example of what can happen with curve shortening flow. So we start with a very awful curve, and let's see what happens as we evolve it under curve shortening flow. So certainly we expect these very sharp curved points here to immediately move to try to smooth things out. And let's watch that in action. So we see the smoothing out behavior that I talked about, and in fact, eventually the curve completely smooths itself out and becomes perfectly round as it shrinks. And so it'll be certainly relevant in the future that one thing we can do as this circle shrinks is imagine rescaling it as it shrinks so it stays about the same size. And what we see in that case is that it just gets rounder and rounder. In finite time, this circle is going to disappear and we reach a singularity. So in general, these flows will have a singularity in finite time. So let's move on to mean curvature flow. It's the same idea. The surface is now going to try to evolve to decrease its area as fast as possible. And so in the image you see here, you have this dumbbell-shaped rotationally symmetric surface. So it's rotated about the vertical axis. And we can see how it will evolve under mean curvature flow. Now, mean curvature flow is a little more complicated in the sense that there are now two curvatures. So in this at this waist, there is this sort of curvature that I'm illustrating with the cursor right now that is trying to push that point outward. But there's also the waist itself, which is curved inward, which is trying to push this point inwards. And so we add those two curvatures together to get the mean curvature, and overall, if whichever one is bigger, will cause the point on the surface to move in that direction. So in this case, it looks like this waist is more curved than the cross section is, and so it will actually be pushed inwards. Okay, so let's run this video and see what happens. And so I'm going to stop it shortly before it stops, and what we see here is that indeed we have a different behavior than what we saw earlier. Rather than becoming rounder and rounder and eventually collapsing as a round sphere, it seems to be trying to split into two pieces. So we can go even a little further and see that really it is really trying to split into two teardrop shapes, and so we were about to reach a singularity here. Another thing I want to point out is that in the zoomed in picture we see that very close to the singularity it looks pretty much like a cylinder. So if we were to do the zooming in procedure closer and closer closer and closer to the singular time we zoom in more and more at the singular point, it'll look more and more like a cylinder. So one thing to remember is that as we dilate, these big bulbs are going to move vertically off to infinity as we keep dilating, as we get closer and closer to the singularity. And so if we keep zooming in and keep getting closer to the singular time, it will look more and more like a cylinder. Okay. So with those examples in mind, we have this general idea of how we can categorize mean curvature flow singularities. We zoom in at the singular point just before the singular time. We get closer and closer to the singular time and zoom in more and more and see what we see. And so in the curve shortening flow example, if we do this, we get a round circle. And if we started with a rounder surface initially, we would get a round sphere in the mean curvature flow setting. But we also saw that this procedure of categorizing a singularity by zooming in could also get us a round cylinder rather than a round sphere once we're in the two-dimensional case. The question is, are there any others? So one thing we know about these limiting surfaces is they have to be a self-shrinker. So they have to evolve under mean curvature flow by dilations. So if I take a sphere and evolve it under mean curvature flow, it will just become a smaller sphere, same shape, smaller size. Same thing with a cylinder. So then the question is, well, are there others? And the answer is yes. So one of the first results is a result by Angenent, finding a self-shrinking torus, which is now called the Angenent torus. And since then, there have been many others. I tried to list as many people as I can that have come up with more examples of self-shrinkers, but I'm sure I missed somebody. So apologies for that. And so let me talk a little bit more about the Angenent torus, which is in some sense the simplest non-trivial example of a self-shrinker. So I have on the left the Angenent torus itself, and on the right I have its cross-section in blue. Next to it we also have a green curve, which if we revolve around the z-axis will get us the round sphere. And we have the orange curve, which if we revolve around the z-axis will give us a cylinder. So this plot on the right is illustrating three cross-sections of three self-shrinkers, and these have all been normalized so that they disappear to the origin after 1 unit of time. So in the rotationally symmetric case, it'll be very important for us to think about both the 3D picture and also this idea that if we're looking at something that's rotationally symmetric, we get all of the information just by looking at this cross-section, and this torus here has this odd-shaped, egg-shaped cross-section. All right, so let's get some intuition about why the Angenent torus must exist. So on the left, so in the middle we have the Angenent torus. On the left we also have a torus that's very thin. It's basically a hula hoop. And on the right we have the opposite. We have a very fat donut, torus. So let's kind of understand what will happen to these under mean curvature flow. Well, on the left with this hula hoop we have this very small meridian circle, and so that means it has very high curvature, and so it will collapse very quickly. In comparison, the ring itself is much larger, has lower curvature, and will collapse more slowly. So what happens is that the meridian collapses really fast, and then we have a singularity that way. In contrast, on the torus on the right, I've tried to make it transparent, so hopefully it shows on the video. You have this thin tube connecting the top and the bottom, and so if we look at that thin tube, it's a very small circle this way, and so it has a lot of curvature that way, and so that inner tube is going to collapse first. So we have a longitude curve collapse first. So on the left, the meridian collapses first. On the right, the longitude collapses first. And so the idea is that, well, maybe if we do something in between that's just right, the meridian and the longitude are going to collapse at the same rate, and then the whole thing is just going to shrink down to the origin by dilations. So it'll be important to keep in mind this intuition picture for later when we discuss stability and index. So this idea that there is this one parameter family of surfaces, and in the middle, just right, there will be a surface that will end up with an Angenent torus singularity.